Okay, great. So I believe everyone can see the screen well. Yeah, so this is the battery repair webinar. Sorry we had to delay it. It was supposed to be last week, but some things came up, so we're holding it today. My name is Jonathan Doan. I'm a senior research scientist at Nuvant, and I've been part of the battery program for probably about 4 or 5 years now. You have my email address. It's listed there. I think everyone that's on the call I have emailed directly. So if you have any questions or concerns, please email me. You have our website. I have my Skype username in case you need to message me for any reason, and we have our phone number down here. So the contact information is located here. We're headquartered in Crown Point, Indiana. That's where we hold the majority of the courses and manufacture our equipment. We also have a research lab at Northeastern University in Boston, which is where I kind of started with the company and started with the professor who is the CEO of the company. So, all right, I'm just gonna any questions on that? And the next slide is actually where we kind of go over the outline of what we are covering today. Okay, so we'll start with an introduction to hybrid battery reconditioning and balancing. This is kind of simple stuff, but I'll try to go through it pretty thorough, but also kind of brief. We'll be talking about voltages, currents, amp hour, watt hour. Most of this is pretty basic electrochemistry, but it's kind of important to learn if you're dealing with these batteries. We'll also go over what type of modules are available and kind of the difference between the nickel metal hydride, which we focus on, and some of the lithium ion batteries, which are used in the electric vehicles. Then we'll go over the actual process of nickel metal hydride battery reconditioning. I'll kind of explain the science behind that. And then we will go over how to use the EVc Battery Reconditioner, how that works in reconditioning the batteries, and how to kind of assemble uh, battery packs based on the module data that you receive from the instrument. Then we'll go over kind of our newest instrument, which is the EVd power tester. So we'll go over a little bit about that, and then we will have a question and answer session along with a chat with Professor Smotkin, who is the founder and kind of runs the company. So, any questions about the outline? What after part two, we'll take a short, maybe 30-minute break, and we can kind of step away. I'll leave the webinar on, but we'll take a short break in between. Okay. Any questions? And again, after the course is over, I'll try to have a copy of it available and then email it to everyone that's currently viewing.
Hey, it's Ahmed. Could we please have a presentation in addition to the recorded video, please, through the email?
Yes, that is what I plan on doing. Yep.
Okay, thanks.
Okay. So first, just a short kind of introduction to Nuvant. So Nuvant was founded in 1999, so we've have about over 20 years of experience in the field. Nuvant kind of began manufacturing this EasyStat Basic, EasyStat Pro also now. It's a smart power supply for batteries and fuel cells, mainly used in research settings, research applications. Then we kind of transitioned to looking or added operando spectroscopy, which is a type of spectroscopy or type of research that allows you to study battery electrodes and fuel cells as they're operating. In 2014, that's kind of when we started our battery sector, this battery reconditioning sector. So the EVc battery balancing equipment was introduced in 2014. And in 2019, that's when we introduced the new EVd power tester, which allows you to power test the full pack before you install into a vehicle. Okay. And currently we have over 100 EVc units in 13 countries around the world, and we continue to develop these reconditioning plans and the technology behind this. Okay, so any questions? We're gonna start part 1. Okay, so yeah, part 1. This is part 1 and 2 are kind of a lot of background and understanding the science of the batteries, and then after that we kind of go over more of how to recondition, how to use equipment, and how to build packs. So in this section we're going to cover nickel metal hydride cells, what cells are, modules, discuss what battery cores are, and then aftermarket batteries in general. Follow this with some battery basics, and then discuss the difference between the nickel metal hydride and lithium-ion batteries. Pictured here is the EVc30. It's connected to a Prius pack. So the EVc30 has 30 channels. What it does is it reconditions each module in the pack individually in parallel with one another. And you can see that it's on a battery pack cooling box because during reconditioning, to prevent the modules from swelling and overheating during the charging process, they have to be cooled with the cooling box and fan. Okay, so to start, you can see over on the left, this is a cell, typical battery. This is a nickel metal hydride battery, and that is the type of battery that's used in the hybrid electric vehicles. You can see it has a nominal voltage of 1.2 volts. Okay, a module, you can see in the middle, that is the typical prismatic module. Prismatic just means it's kind of shaped like a square or a rectangle. The prismatic module, this one is the one that's used in the Toyota Priuses, Toyota Camrys, the Prius C, and all sorts of other, mainly Toyotas. I have a list of actually all the vehicles and which modules that they use. And so these consist of 6 cells. You can count them 1, 2, 3, 4, 5, 6. And all of the cells are connected in series. So when cells are connected in series, you add the voltages up. That's why this module is 7.2 volts. Okay. And over here we have a core or pack. This is a Toyota Prius, which consists of 28 modules. And you can see that the voltage is 202 volts. The Toyota Camry hybrid has 34 of these modules in series. Okay, and down here you can see the chemistry of the batteries. So you have the negative electrode during discharge, which is the metal hydride. Okay, this is the reaction. The metal hydride combines with the hydroxide and forms metal and water, and gives off an electrode. So that's the negative electrode. And over here you have the positive electrode, which contains the nickel. So if you add the voltages together to get the full cell voltage, it's 1.35. But this voltage here is the voltage of a fully charged cell. So nominally they say that the cells are 1.2 and the modules are 7.2. But a fully charged cell is 1.35 and a fully charged module is 8.1. But we will discuss these cells and modules in terms of their nominal voltage, which is 1.2 and 7.2. Okay. Yeah, feel free to ask questions at any time. All right, so the next slide here, we have other examples of nickel metal hydride modules, we have the Prismatic on the left, which we showed with the six cells. The capacity of this module is 6.5 amp hours. And I'll kind of explain what that means, but that is the amount of charge that this module can hold. Over on the right, we have the cylindrical modules. These are the ones that are found in the Honda Accord, Honda Civic, Honda Insight. These are not as robust as the Prismatic modules, and I'll kind of discuss that a little later on too. But they also have a rated capacity of 6.5 amp hours, and they also have 6 cells in series, so that is also 7.2 volts. You can also have different numbers of cells within modules. So for example, the Ford Escape, you see down below, has 5 cells, and that combines to give you 6 volts. Okay, we'll focus on the Toyota Prismatic modules in this webinar, but we have reconditioning plans for every type of nickel metal hydride module. We have a lot of users in New Zealand and Australia, and they have modules that actually consist of 12 cells. So it's similar to the Prismatic module you see on the left, but it's a lot longer. It has 12 full cells in it. Okay, any questions on that? Okay, good. So the next, this slide here kind of shows the Toyota Prius pack. You can see the pack within the enclosure, the cover, and then you can see it removed from the enclosure. Okay, again, there's 28 modules, nickel metal hydride modules in this pack, and each module is 7.2 volts again, 6.5 amp hour. They are connected in series, meaning that the negative end of module 1, for example, is connected to the positive end of module 2 with the bus bars. The voltages, because of that, the voltages are all added. That's why this pack is 202 volts nominally. The next slide here kind of shows how the vehicle separates the modules. So here you can see that there are 28 modules, right? Each of these kind of rectangles. But the vehicle, the Toyota Prius and the Camry, they divide the pack into blocks consisting of 2 modules each. Okay, so in this case, there's 28 modules, which means that there are 14 blocks. The POA80 code that appears, the onboard diagnostic code, that appears saying that your pack is bad when the voltage difference between the battery blocks is higher than standard, which is more than 1 volt, we believe. So the vehicle doesn't actually measure or monitor the voltage of each module. It separates them into blocks. Okay, so it would be like block 1 is 14.4, block 2 could be 14.5. And when the difference between any of these blocks, for example, block 1 could be 15.5, right? And then block 8 is 14.5. There's a difference of 1 volt. That's when the check engine light comes on. Okay, and we'll discuss this in more detail a little later on, but just remember that the vehicle only reads the block voltages, not the individual module voltages. And here we have the example of the Toyota Camry, which is similar to the Prius, same modules, you can interchange them, but it contains 34 of the modules, and they again are connected in series, similar to the Prius. Okay, that is why all of the voltages are added. And here again, the Camry consists of 34 modules, but there are 17 blocks because you have 2 modules per block. So any questions on that?
I have a question.
Yes.
If there was a problem in one battery in each module, should we remove or replace all the block or the one battery?
I will go over that a little later on, but no, you do not want to. So some users just kind of read the voltages with a voltmeter, and then you kind of take the bad module out and replace it with a good one. But that's the incorrect way to build a battery pack. I'll go
Okay.
over what you should be doing, because when you do that, you still have an unbalanced pack. You're just kind of replacing a bad module within your pack. So
I think.
okay, and just to make sure everyone can see the screen properly, correct? We're on slide 10 right now. Okay. Yeah, so I'll go over that is covered in the presentation too. So any other questions? All right. So here, this is the next slide, which is the full list of, or a mostly complete list of the nickel metal hydride battery vehicles. These are the kind of the most common, especially in the US. We have a lot of other vehicles overseas. They kind of use the same battery packs, but they're known by different names, different models. So this is kind of a useful resource. And again, I'll have this provided to you after the webinar, so you can kind of look and get a feel for what vehicles there are. But the main vehicles that a lot of our EVc owners deal with are the Prius, the Camry, the Highlander. But note here that the Highlander has 8 cells per module. Okay, so it has 9.6 volts. The Highlander is a little more complicated. Obviously, you have to use a different reconditioning plan because the voltage is higher. But it also contains 30 modules per pack, and they're kind of divided up in a weird way. So we do have the full instructions on kind of how to take apart a pack, put it back together for the Highlander. And kind of some of the largest packs that you kind of deal with are the Escalade, these SUVs here. So the Tahoe, for example, it has the 6 cells per module. That's the Prismatic one, the same as the Camry and Prius, but they actually have 40 of them instead of 28 or 34. So your voltage is a lot higher. Okay. All right. So yeah, this is the list, and I'll provide this a little later on. We're gonna kind of go into the battery basics now. So I'll discuss kind of what voltage, current, and etc. are. So how do I remove this drawing tool that I just kind of put together? Normal non-drawing mode. And let me, erase all drawings. Okay. So here, these are just some of the basic battery terms that we'll be using. Voltage. So voltage, most people think on this webinar know what voltage is. It's basically just the difference in electric potential between the positive and negative terminals. So in a battery, you have 2 electrodes, and the difference between the positive and negative electrode, that gives you your voltage. Okay. And that is specific to kind of the chemistry of the battery, what the battery is made of. You have current, and current is given in amps, units of amps, and that is the rate of flow of electric charge. Okay, so your current can either be a charging current or discharge current, depending on what you're kind of doing with the battery, if you're charging it up or discharging it. You have watts, which is a unit of power equal to the current flow of 1 amp with the voltage of 1 volt. Okay, so 1 watt is equal to 1 volt times 1 amp. You can see down on the left with the formula there. Resistance. Resistance is the measure of opposition to current flow. And again, these terms, I'm going to explain them with some figures in a little bit. So I'll explain it a little further. You also have amp hour. So amp hour is one of the main terms that we'll be using when discussing the kind of the health of the battery, right? So amp hour is the amount of electric charge. Okay, so it's equal to the charge of 1 amp flowing for 1 hour. So if you have a battery, and let's say you have a battery and you're discharging it at 1 amp for 1 hour, you will have discharged 1 amp hour. Okay, if you are discharging that battery at 2 amps for 1 hour, you have discharged 2 amp hour. Okay, so that formula is right here. Amp hour equals current times time in hours. Watt hour is a little more complex. That's actually how much energy that battery holds, not just charge. And in order to get watt hour, you can multiply the amp hour, the capacity, or the amp hour capacity, times the voltage. Okay, so again, these are just the terms. I'm kind of prepping you for the next couple slides where we'll actually explain the battery. And I will be using a metaphor of kind of water. All right, so, and any questions before we start this? Okay, so voltage and current, it's analogous to pressure and flow rate. All right, so if you imagine these are two kind of water tanks. All right, the voltage is the height of the water. All right, and the current is the amount that's flowing out or the amount that's flowing in. Okay. So when the spout over on the left, when the spout is first opened, the flow rate of the water will be at the highest. Okay, because the pressure or the voltage is at maximum. All right, so if you have a very tall or high cylinder, a high level of water, it will come out faster than when it reaches toward the bottom. All right, so as the water drains, the pressure goes down, as does the flow rate. Okay. Over here on the right, we have the same volume tank, the same amount of water, but if you have a larger spout or allow more water to flow through, that's equivalent to having a higher current. That's why you can see the arrow here is larger than this arrow. Okay, so remember that just voltage is the pressure that drives the current. It drives the flow. Okay, any questions on that? Okay, so this next slide here, you kind of have the same voltage and currents, but now we're going to discuss what resistance is. So basically, resistance is opposition to flow. It's the opposition to current. If you look over on the right, you have a regular pipe, okay, flowing, and a regular pipe has less resistance. Okay, if you have a kink in the pipe where the flow is compressed or lessened due to this area, you have more resistance. Okay, so the narrow pipe resists the flow of water more than the wide pipe. Okay, in general, the circuit with higher resistance, or the narrower pipe, will allow less charge to flow per time. Okay, you get less current. All right, so within, in regards to the battery, okay, batteries have an internal resistance. You want to basically minimize that internal resistance. If the internal resistance of the battery is too high, that battery cannot accept or deliver charge, right? So it won't perform well in either charging or discharging applications, okay? So you want to minimize resistance. Resistance is bad. Okay. So let's kind of discuss charging batteries now, okay? So on the left, let's imagine that you have two batteries, same height / voltage, which means that they're the same type of battery chemistry, but battery A is a little wider. Okay, so it can hold 8 amp hour. Okay, and battery B, for example, can hold 5 amp hour. Okay, if you charge at 1 amp, okay, right now they're completely empty. If you charge at 1 amp, okay, after 3 hours, you will get 3 amp hours, right? That's simply 1 amp times 3 hours. You're going to get 3 amp hours of charge in the battery after charging. However, you can see that the voltages are going to be different, okay, because battery A has a higher capacity than battery B. Okay, so this is kind of an example of charging kind of simplified. But what would happen if you filled the container, the batteries, and charge them more quickly? Okay, so at this different rate, all right, we have the same batteries on the left. We're still charging at 1 amp hour. This should be 2. Let me change this with a pen. I messed up something on the slide. This should be 2 amps. Okay, this should be 2 amps, and then after 3 hours at 2 amps, you will have 6 amps here. Okay, out of the 8 amp hour. You have 6 amp hour out of the 8 amp hour full. Over on the right, you will only have 5 amp hour. Okay, because the battery can only hold 5 amp hours. So you've overcharged the battery by 1 amp hour. Okay, in general, that will damage the battery because that extra 1 amp hour, depending on your charging rate, and in this case it's 2 amps, that's pretty high comparative to the capacity of the battery. You can damage the battery. It will swell, and gas will build in the battery. It'll also get hot. Okay, the extra energy that's used to charge the battery will expand the battery and heat up the battery. Okay, this is an example of charging and overcharging again. Any questions on charging? And we're gonna cover discharging next. Okay. So in discharging the battery, sorry, let me just get rid of this, erase all drawings. In discharging the battery, okay, so on the left we have the same batteries, the 8 amp hour and the 5 amp hour capacity battery, but we're starting with them fully charged. Okay, we're going to discharge each battery at 1 amp. So after 3 hours, battery A will have 5 amp hour left because remember to measure the amount of capacity that's discharged, you multiply the discharge rate times the time. So 8 amp hour minus 3 amp hour gives you 5 amp hour. And over on the right, battery B, you're left with 2 amp hour. Okay. So similar, this is an example of discharging. We're going to now go to higher current. So it's going to be similar to what we did on the previous charging. So in this case, we're going to increase the current, the discharge current, to 2 amps. Okay, after 3 hours, you'll be left with 2 amp hour in battery A. In battery B, you basically have over discharged that battery. It's going to be about 1 amp, it's going to be around 0 amp hours left. Okay, so this is what discharging and charging is. Within the vehicle, okay, that's using the hybrid battery, you will be, during normal operation, the battery is charged and discharged, but it's a very small percentage of the actual battery capacity. And we'll discuss how that affects the battery and the performance. Any questions on charging and discharging? Okay, Good. So the next slide here is C rate. So C rate is what battery researchers or battery people use to discuss the battery capacity. So C rate is a measure of the rate at which a battery is discharged relative to the maximum capacity. Okay, so basically when they say 1C for a battery, that is the current that discharges that particular battery in 1 hour. Okay, so that's a little confusing. Let's look at these examples. So we have an 8 amp hour capacity battery. We have a 6.5 amp hour capacity battery, and a 1 amp hour capacity battery. Okay, you can see this, the sizes are different. For the 8 amp hour capacity battery, 1C is equal to 8 amps. Okay. For the 6.5 amp hour capacity battery, 1C is equal to 6.5 amps. And for the 1 amp hour capacity battery, 1C is equal to 1 amp. Okay. And in this case, whatever you do to C, you do to that current. So let's go back to the 8 amp hour capacity battery. Remember that 1C is 8 amps, right? Because if you want to discharge that battery fully in 1 hour, you have to go at 8 amps. What is 0.5C? Okay. Remember that whatever you do to C, you do to the current. So for this particular battery, if we want to know what 0.5C is, you'd simply multiply the 8 amps by 0.5, you get 4 amps. Okay. So for this battery, 0.5C is 4 amps. Does everyone understand that? Okay. Let's look at the next one. We'll kind of do another calculation like that. So remember that this battery is 6.5 amp hours. Okay. Let's jump more. Let's say, what is 10C? Okay. For this particular battery, 1C is 6.5 amps, right? So 10C would be 65 amps, right? Does that make sense to everyone? Because if 1C is 6.5, if you're trying to figure out what 10C is, you simply multiply the current by 10. That's how you get 65 amps. Okay. And in the case of this 1 amp hour capacity battery here, if 1C is 1 amp, let's just, for example, what is 2C? Right, and if to get what 2C is, you simply multiply this current here by 2, so you end up with 2 amps, okay? So for this battery, 2C is 2 amps, okay? This is kind of important because when you charge the modules, you don't want to charge it too quickly when you approach full charge, okay? So when you approach full charge, that current that you're charging at must be tapered down, okay? If you don't taper it down, you'll get a lot of heat dissipated in the battery, and you'll get swelling due to oxygen evolution. Okay. So in this case over here, on the left, you can see a regular Toyota module kind of looking from the top. And then you can see what happens if you charge too fast, so too high of a current, and you don't use the cooling box and clamps. Okay, so this is a module that I made explode kind of on purpose, obviously. So I did not clamp the module, or I did clamp the module, but I didn't cool it, and I used too high of a current. This is something that I did, 5 years ago when we were first testing out and trying to experiment with these nickel metal hydride batteries. Do note that these nickel metal hydride batteries, though, they're different from lithium ion batteries. So you've heard how lithium ion batteries catch fire. That's because the liquid in the lithium ion batteries is flammable. Okay. However, the nickel metal hydride, batteries use a water-based electrolyte, and therefore the nickel metal hydride batteries, even though they can swell and kind of explode like that to the sides, they will not catch fire. Okay, they are not flammable batteries, unlike the lithium-ion. Okay.
I have a question.
Yes, go ahead.
Yeah. What do you mean by the phrase too fast? Is there a special range for the word too fast to know if this is fast or slow?
Yes. So we'll discuss that too. But when you start getting close to say 80% of the charge of the battery, from 80 to 100%, you want to go at about half an amp. Okay. Which half an amp is less than 0.1 C. Okay, so remember that for these modules, right? They are 6.5 amp hour. So in general, you want to go when you're approaching full charge, you want to go at around 0.1 C or less. So in this case, remember 0.1 C is, if this is 6.5 amp hour battery, 0.1 C is going to be 0.65 amps. So we actually go at a lower current, a lower discharge rate when we get that high. We go at 0.5 amps. Okay, that's to prevent the swelling.
Okay, I see. Thank you.
Okay. All right. Any questions on?
I have a question. After the webinar is over,
Yes.
are you going to email us the recording of this webinar?
Yes. I will send you. I'll try to provide a link for the recording, but I'll also send you the slides.
Because the thing is, I am in Pakistan, about 12,000 miles away.
Mm-hmm. Right.
The net is, the voice is breaking down.
Okay. Yeah. Yeah. If you're having trouble, I could send you this recording afterward, and then we can
Yeah, that would be great.
talk,
That would be
too.
great.
Okay. All right. Any other questions? Okay. So yeah, that was C-rate. We're talking about the how to measure current based on the battery charge capacity. And the next slide here, we will discuss, or actually just kind of look at the actual specifications of the module. Okay, so I found these a couple years ago online from the data sheet of these actual batteries. And this is a kind of a good resource. We won't discuss every aspect too deeply, but what I really wanted to note is that is two things, okay, and they're highlighted in yellow. The first thing is that the capacity of the battery. Okay, how do they rate the capacity?
Hi, Jonathan.
Yes.
Jonathan,
Yes. Hello.
can you please go back to the previous slide? I just missed something.
Okay.
Can you go back to previous slide? Okay, now
here,
you
yes.
just said that when you reach around 80, can you hear me?
Yes, I can hear you. Go ahead.
Yeah, I say you just mentioned that when you reach 80% of charging the battery, you need to reduce the ampere.
Yes.
Is this being done automatically by the charger, or we need to do it manually?
With the EVc 30. So with the EVc 30, and I'm going to discuss this later.
Yes.
We pre-make plans, and all you have to do once you connect the battery and start the plan is just press play. So I have all the plans specifically designed with all of this information in it. Okay, so all of this background information is important for you to understand, but you don't actually have to utilize this information when you are running the EVC30 or any of the EVc instruments. With the EVc instruments, it's literally automatic. You kind of just press play, and then the instrument runs the plan that you have selected. Okay, and you don't have to monitor it. The full reconditioning takes
Thank you.
about 20 hours, and then after 20 hours, you kind of come back, and it'll be finished, ready for you to look at the data. Okay. Okay. Any other questions? Okay. So let's go back to the next slide, which is, again, yeah, the Prismatic module specification. So the first thing we want to look at is this capacity, right? So this is how Toyota rates their batteries. Remember that we said that they're 6.5 amp hour. How do they determine that it's 6.5 amp hour? What they do is they have the module put together, fully charged, a brand new module, and then they discharge at 3.25 amps down to 6 volts. Okay. When they discharge at 3.25 amps down to 6 volts, they get a capacity of 6.5 amp hour. Okay. In other words, okay, imagine this is the voltage of the battery. This is time. Okay. And we are discharging at 3.25 amps. Oop, there we go. Okay. So the voltage of the battery, a typical discharge curve kind of looks like this. Okay. So this is the voltage of the battery. Let's say brand new, let's say it's about 8 volts. And remember, we want to get down to 6 volts. Okay. If you're discharging at 3.25 amps and it takes, remember this is time. Let me write time out. Time. This right here, when it hits 6 volts, is going to be 2 hours. Okay. And we know that because 6.5 amp hour is 3.25 amps times 2. Okay. Does that make sense? Basically, we know the way that Toyota does it is they use the discharge current of 3.25 amps down to 6 volts. Okay. And they get a capacity of 6.5 amp hour. So we can determine that that takes exactly 2 hours. Right? Does that make sense? The main reason I'm bringing this up is because we, in the reconditioning plan that we designed, we use the same method to rate and diagnose the batteries after reconditioning that Toyota uses. So they, the instruments, the plans, discharge after they fully charge the battery, discharge the battery at 3.25 amps down to 6 volts. Okay, and then the capacity that you get in the data is the capacity that we have for that module. Okay. So any questions there? Remember that the capacity of the rated capacity of these modules is 6.5 amp hour. Okay. Down here too, remember we just kind of discussed the charging currents, why you want to go slow. Toyota specifies that you have to taper. See, it says 6.5 amps, tapering down to C over 10 or less. And remember that C over 10 is 0.65. But we actually go lower, okay, when we approach the full charge. Okay, we use 0.5 amps. Okay. The last thing that we kind of want to note on this page, unless you have other questions, is the internal resistance. Okay. So the internal resistance of a brand new module is about 8 milliohms. Okay. And what we recommend is if you have any resistance that's much higher is a module that we kind of remove and do not use in our packs. Okay. So, and we'll discuss that when we get to the battery building, the pack building part. Okay, so any questions on this specification?
I have a question.
Yes.
Why they have to discharge the battery before measuring the capacity?
What do you mean? So this is when they first rated all the batteries. So they actually don't rate every single battery. This is just how they determined that the battery capacity was 6.5 amp hour in the beginning.
Yeah, I've mentioned here the voltage is 7.2 volt, right?
Correct.
Okay, why they measure the capacity at 6 volt?
No, so you measure capacity by taking the fully charged battery, okay, and then discharging it down to 6 volts, right? So when you discharge it, you can measure the current and measure the time, and that's how you get the capacity of the battery.
Okay, I see.
Yeah.
Okay, thank you.
Remember that, and just to kind of explain again, remember that voltage is based on the chemistry of the battery, right? And the capacity is more associated with the size of the battery, right? The amount of material that's within the battery. Okay. So yeah, remember that in order to, you cannot, so that's kind of one of the main things that we get at is you cannot measure the capacity of a battery by just taking a voltmeter and measuring the voltage. That only gives you voltage. That does not give you any other information besides voltage. Okay, because you don't know what the state of charge of the battery is, and you don't know what the state of health of the battery is, of the module. That's why we do kind of full diagnostics to give you the voltage, the current, the internal resistance, the amp hour, and the watt hour energy of each module after reconditioning. Okay. Okay. Any other questions on this? All right. So yeah, this slide here is an example of how you can calculate the watt hour energy. Again, the instrument does all of this for you, but just kind of as background, we'll show what that really means. So remember that watt hour is your amp hour times your voltage. Okay. In this case, there's two things I want to note. You can estimate the watt hour energy based on the midpoint voltage. Okay, so what you can do is basically take your amp hour value down here, which is 6.4, okay, and multiply it by your midpoint voltage to get an approximation of what the watt hour energy is. In this case, the EVc software actually calculates the actual watt hour energy, so you do not need to actually do any calculation, but this is kind of just an example of what it really means. Okay, any questions on energy? So when you are kind of rating your batteries and or your modules and trying to build a pack, we use kind of either watt hour or amp hour to determine the health of the modules. Okay, either amp hour capacity or watt hour energy. Okay, so here I'm just kind of briefly describing the difference between nickel metal hydride batteries and the lithium-ion batteries. Remember that nickel metal hydride batteries are mainly the ones used in hybrid vehicles, okay? And lithium-ion batteries are mainly used in the electric vehicles, the fully electric vehicles, right? So the reason for that is that nickel metal hydride batteries have a lower voltage. Remember, per cell, nickel metal hydride batteries are fully charged about 1.4 or 1.2, and lithium ion batteries are 3.7, 3.9 volts. Okay, so they provide a lot more energy at a lower capacity. All right, that's why. So remember that electric vehicles rely solely on the battery to power the vehicle, but nickel metal hydride batteries, which are used in the hybrid vehicles, they're used for more of assisting the engine, right? So the battery's activated when you accelerate and it's charged when you brake. In this case, so if you note this picture, the nickel metal hydride battery, it only has 9.1 watt hour, even though the capacity is 6.5 in this case. The lithium ion battery has a much higher voltage, and remember that's a feature of the chemistry of the battery. And the capacity, the amp hour capacity is 5 amp hour, right? And that gives you 19.5 watt hour. Okay. So this is kind of just to note that lithium ion batteries have higher watt hour energy, but in general the capacity is lower. Okay, the charge, the amount that it holds, it's just that each per charge the energy is a lot higher. Again, this is kind of the same figure, the same idea, but I'm actually showing the discharge curves. So with A, which is the lithium ion battery, you can see that the midpoint voltage is a lot higher. It's about 3.5, while in the case of B, it's 1.2. So even though B has a much higher amp hour capacity, you can see that. So if you look at the box that we made, the box A is larger in area than box B. Okay, so that means that it has a higher watt hour energy. Okay, so now let's talk about the actual vehicle. Okay, so in normal hybrid electric vehicle operation, let's say your engine is idling right now. Okay, so you're driving your vehicle, the engine is idle, and your charge level is about 76%. Okay, typically within the Prius, it'll sit at about 80 to 60%. So when you accelerate, okay, that discharges the battery. However, in hybrid vehicles, you're only discharging a very small portion of the battery each time. So you went from 76% to 68, maybe even higher. So it could be even like 70%. Okay, the charge level. And then when you brake, you charge the battery up a little more. So now you're at about 75%. So in general, these charge discharge cycles, they only use about 10% of the battery capacity. Okay, but it happens many times during a trip. So if you're driving and in your vehicle for a long time, you could be accelerating and braking from a stop, 50 times a trip if you're going somewhere pretty far. So the vehicle gradually gets used to that small or shallow charge discharge cycle, right? The 10%. Okay, and in the next couple slides, I'll kind of show what that means, but this is what is called the memory effect. All right. So the small, shallow charge discharge cycles, okay, in nickel metal hydride batteries is what causes the memory effect. And the memory effect has been seen for a long time in both NiCad, nickel cadmium, and the nickel metal hydride batteries. And we know that it occurs on the nickel electrode, the positive electrode. Okay. And we'll go over the memory effect in the next couple slides. So Any questions on this? This we kind of just finished part 1, which is kind of the longest real part of the webinar. So any questions on this? Okay, and I have a brief summary here. So again, yeah, I'll send all these slides and hopefully the video of this recording to all of the users. Okay. All right. So any yeah, is there any questions on this first part? If there are no questions, we're gonna start section 2. So section 2 is a little shorter, but after section 2, we'll take maybe a 30-minute break. I'll leave the presentation and meeting open, and then we will continue after that. So let's go ahead and start section 2 at the end of this slide.